Right. Well, hello, good evening everyone. Thank you very much for coming along this evening, and thank you very much for everyone who's on Zoom and YouTube. Lovely to have you all. A few procedural points first of all. Can you make sure you've signed the logbooks, because we do get a certain amount of money from IOM3 for your attendance. Could you please pay attention to the signage for the fire escapes and such like. If there is anything happening, just follow the lights and it'll take you to the appropriate place to gather. Secondly, can you please switch off your mobile phones? There will be a penalty for anyone whose phone goes off. It has never been applied yet, but there's also first time. So there we are, more or less. Was there anything else I'd like to say? Yes, I'm sure Richard wouldn't mind too much if you don't take photographs and don't tape or record anything, and I'm sure he'd be quite happy to give you a transcript of it if at any time you would like to have that. So there we are. Let's move forward on that now, and I think the first thing we're going to have to do is to ask for any apologies for non-attendance. I've got, let's see, who have I got? I've got Rick Smith, I've got Stuart Porthouse, Ian Cameron McIntosh, who has actually turned up now, so to strike him from the record, he wasn't expected. Malcolm Tilley and Simon Brooks. Have you got anything at all up there?
David Douglas as well.
David Douglas, right. We'll take a note of that. That's excellent. Right, in that case, I'll pass you over now to Andrew to give a few little adverts and things that's happening over the next few months. Andrew?
Brilliant. Well, thank you very much for Richard for agreeing to give the talk. Just a few notices as per usual. Our last month's lecture was on probing ion mobility in solid electrolytes or solid state batteries. It was a fascinating lecture on all things to do with lithium and crystallography and NMR, which was really, really exciting. Unfortunately, I think the weather are putting people off, but it's not been putting people off viewing it on YouTube because it's been very popular. Questions by Tom Mulholland, voted thanks David Granger, and of course closing remarks to President. So if you can take that as a true record of the meeting, Steve?
Yes, indeed. Lovely.
So just to let you know about our upcoming events, our March lecture will be given by Professor Jeroen van Heunen on modelling mine water heat extraction. This is a large project which has recently received both, I think, EPSRC and Natural Environment Research Council funding to look at the old mine workings around the north, and particularly County Durham, and see what their geothermal potential is. Our institute has been helping out with this, and so it's going to be fantastic to see some of the initial results from this research project. Our April Institute lecture is on the verge of being confirmed, but it's going to be on the geotechnical engineering of the A1. There will be a lot of bridges involved, which is going to be very exciting for all the civil engineers, and we're also currently just working on the final details of the field trip as well, so stay tuned for that. Our May Institute lecture is going to be on the fabrication and practical applications of terahertz devices. In layman's terms, this is going to be to do with all sorts of antennae applications and things like that. So that's going to be really interesting, and hopefully we will be being joined by the local IET group as well. Don't forget, you can follow us online. We're on all the major platforms, Twitter, Facebook, YouTube, which is growing by the day. So don't forget to like, share and subscribe. And if you want any more information about our institute, just go to moneyinstitute.org.uk. In terms of our events and activities, you're at one of our excellent lectures. Do please keep turning up. Our annual dinner is only a few more weeks away at the start of April. If you haven't signed up yet, do let us, do please get in contact. If you'd like to sponsor it in any way, if you happen to be part of a company, do also get in contact about that. We've got social events pretty much every 2 months now, and we're working on more. And also we've got a field trip, a couple of field trips being planned, one to Woodsmith Mine, hopefully later this year. But also we've got the discoverer of the giant millipede of Northumberland, and he'll be turning up again at the start of April, coming all the way up from Cambridge for that. So do please, if you're not already a member, send in that membership application, and you'll get all the invites to all of our events. as well as plenty of other excellent opportunities. So just a reminder, mininstitute.org.uk/membership, and we'll see you soon. There we are, Steve. I'm really looking forward to this. I saw one of I suppose the last slag pours out of Redcar blast furnace. So to see what the future of these furnaces is going to be is really exciting. So I'll hand back to you, Richard.
Lovely. Thank you very much, Andrew. That's the procedural stuff over. Now let's get to the real meat of the evening. Tonight's speaker is Dr. Richard Curry, and he's going to give us a talk on sustainable steel manufacture and the possible future for the North East Steel. Dr. Richard Curry is with Sustain Steel in Swansea University, and Richard is the Research Programme Manager for Sustain, based at Swansea. Richard has a background in electronic engineering, biomedical sensors and holographic lithography. Richard has worked at both academic and industrial research and managed several research groups within Tata Steel Research and Development. In 2013 and 14, Richard reshaped Tata Steel's T-Style laboratory, ready for a spin-out as an independent industrial research and development facility. The spin-out was successfully launched as the Materials Processing Institute, MPI, in December 2014. Richard left his role as Director of Operations of MPI in 2018 to join the Sustain team. Richard's interests lie in circular economy, decarbonisation and industry. And even more so, he's from the North East, so he's even more welcome. Richard, I've spoken enough. I'll hand it over to you.
Thank you very much. Yes, I'm a Horden Colliery lad. Although a lot of the work I'm doing now is in South Wales, it's you know, it's a UK benefit. It's not just for the South Wales region. It's to try and you know, reignite the steel industry within the UK, and you know, make sure that we can. I'm not going to use Build Back Better because I'm sick of hearing that, but it's you know, we do need to bring industry back, and we need to bring back all the supply chains and everything that go along with it. So with that, so I'm going to give you a quick intro to, you know, where we are, and also, you know, a bit of information about Sustain as well, and then I'll go into some of the projects that are, I guess, applicable from like the energy and the sustainability side of things. Sustain's a much bigger project, as you'll see from the description I give, than I'm going to go into today. And then I'd invite anybody to look us up on the internet. It's www.sustainsteel.ac.uk. If anybody has any questions that don't get answered in the session, you know, please feel free to contact me. And if you're interested in Sustain, we can sign you up to the info mailing list, and you know, you can find out a bit more. So I'll get on with it. Okay. So I just wanted to just give a bit of a background. I mean, as you heard from the description of sort of my path into steel, if you talked to me, 12 years ago and said I'll be working in the steel industry, I'd have probably, you know, shook my head. But when I actually did get involved in steel, I realised just how important it is. You know, it underpins everything within the economy. So if it isn't made of steel, it's made with steel. It's such a versatile material. So if, you know, just as a quick intro, for construction, I mean, you can see the numbers there, you know, 88.7 billion. Energy and security, 12.5 billion. Transport, 14.5 billion. You know, 5.2 billion for your trains, 8 billion for your aerospace, and then you've got your commodities and, you know, your tubing and your packaging, engineered goods, 18.4 billion. So, you know, that's that adds up to quite a long telephone number. And you know, without steel, our economy would be we wouldn't have one, basically. So our modern day existence, you know, the nice lifestyle we have, the freedom of transport, everything is all based on steel. So some more facts. I mean, these are just taken from the World Steel Organization. You know, 75% of the 3,500 steel grades that are in use today didn't exist 20 years ago. So, you know, within that 20-year period, we've developed all of these grades. And I'm actually going to go back and say, do we really need to have all these grades? Because having all of the elements that are added to them to give them these properties make them far more difficult to recycle. So, you know, we might have to take a step back. We might have to have thicker car body parts, things like that. Who knows? And of course, the amount of steel in use in the world today, 200 kilograms per person. I mean, it's unreal, isn't it? So just take those numbers into account. There'll be no electric mobility without steel. It's an essential material for construction. And, you know, we really need to start to see if we can reduce the amount of carbon, because it's so widely used, so ubiquitous. The amount of carbon, it's roughly, you know, twice the amount of steel that we pump into the air. So, you know, we're talking over 2 billion tons of carbon dioxide that we're pumping into the air all of the time. And we really need to do something about that. So, if we look now at the UK, and you look at the Kyoto target, the blue line is, you know, our emissions, and it looks as though we've actually, you know, dropped below that target, but in reality, we haven't. We're offshoring a lot of CO2, so we're patting ourselves on the back, and we're saying that we're doing such a good job, but in reality, we're closing down production, losing jobs, losing control in this country, and then offshoring it. So we're not having an impact on the CO2. We're not actually, you know, keeping control of these things. And it's the Western world, it's, you know, it's the UK, it's the States and Europe that are going to make a difference. I don't think the Chinese and Indians are really, I mean, they're in a totally different stage of development in terms of industry than we are. I don't think they're going to be really focusing on that. And, you know, we can see recently with the climate convention that wasn't the case. So we need to keep control, and we need to make sure that we do actually lower the CO2 that we emit, you know, within the UK. Another thing we have that's not going too well is the energy crisis. So part of this offshoring, we're shutting down power plants. We're reducing the amount of CO2 that we put into the air, but we're actually, you know, we're not going to cope with the next generation of electric vehicles, the next generation of, you know, electric trains, things like that. It's electric industry. So if we shift from blast furnace to arc furnace, are we really going to be able to cope with that? And recently in the European electric steel seminar series that was on earlier in this year, there was several companies, one of them being Liberty Steel, who are, you know, they're having some problems other than this at the moment. But they were reporting that they were getting spot changes in electricity prices through demand, and it was going, you know, orders of magnitude up within days or hours or whatever. So they have to stop production. If we look at the graphs on here, so if you're interested in this, it's all published online by Dr. Grant Wilson from Birmingham, and he keeps a log. This is a bit behind the times. I apologise for that, but if you look at the most recent, you can actually see the drop in liquid fuel use. Sort of like you've got the 2020 thing there. You can actually see how that's picked up again. But that's due to COVID, obviously. But if you were to take the gas usage and the liquid fuel usage, and then sort of stack that up on top of the electric usage that we currently have, we'd need to have four times the amount of electricity supply that we currently do. So if everybody today was to use electric vehicles, and we were to, you know, go to electric heat in our homes, industry was going to switch to electricity rather than gas, all the lights would go out. So you know, we're putting ourselves in a very strange position, I think. And on one of the final slides, I'm going to, you know, add to how that is going to be actually stopping us from hitting the targets that we need to hit. But I'll get onto that. I'll get on that later. And of course, we've got the plastic crisis as well. So we're using a lot of plastic across the world, and it's all being thrown away, ending up in the oceans, landfill, things like that. It doesn't degrade. It's a carbon source. It could be a second bite of the cherry. We could use carbon capture and utilisation with that. And the other problem we have as well, that I haven't put a slide up on here, is fossil fuels. So the oil that we use for petrochemicals and for pharmaceuticals, you know, plastics, all that sort of thing. If we stop oil production, then we're going to have to get the carbon from somewhere else. So where do we get that from? Can we use CO2? Can we get the carbon from the CO2 to actually replace that? It's one of the projects in Sustain, as you'll see, but we've got a lot of work to do to get where we need to be. So Sustain's part of a bigger set of projects that include Comet and the Rapid Alloy Prototyping Project based at Swansea. We also have, so that's developing new alloys, new alloys with more additions, and also, you know, alloys that have less additions, where we use, you know, heating and rolling techniques to get the same properties without using these alloys. We also have the specific project, which is based on printable photovoltaics, so rather than make them from silicon, which is very damaging to the environment. You've got to dig the quartz up, you've got to process it. It takes a lot of energy to do that. Some photovoltaics, you'll actually get less energy out of them at the end of the day than you put in to make them. So having something that's polymer-based, inkjet printable, printable on steel, you know, which has been trialled successfully, as one of the alternatives. And the ABC project, Active Building Centre, there's been a street of houses put up for low-income families in Neath as a trial, where they have basically zero energy bills due to, you know, using novel uses of steel for heating, and also a technique using basically a salt with vermiculite that has an endothermic, exothermic sort of reversible reaction. So in the winter, when it's basically a water absorption reaction. In the winter, when the cold, wet sort of air comes in, it starts the reaction off, and in the house they get hot air, warm air, and then in the summer it dries back out again, and it cools, has a cooling effect. So it's little bits of technology like that all put together. And then there's a Sunrise project where we're building similar sort of buildings but out in India, where they don't have access to power, and that's it's quite successful. So, you know, you've got Indian homes that are you know, cooled, and also have electricity generation when they're, you know, way out in the sticks and away from any sort of local power generation. So more about Sustain. So we're very lucky to get Sustain. Sustain was, it's an EBSRC project, and EBSRC don't usually invest in steel. So government funding, low TRL, and the project, so it's a 7-year project. We're about 2.5 years through now, and it's 32 million over 7 years. And that's, it's 12 million from EBSRC, and the rest has come from industry and local authorities, things like that. We've got all of the major steel companies in the UK, so Liberty Steel, Celsa, Forge Masters at Sheffield, British Steel and Tata Steel are all part of that project, and they've all invested quite heavily in that. And the point of the project is to do two things. We've got two grand challenges. The first challenge is to basically find a solution for net zero steel making and net zero carbon steel making, and also what we call smart steel making, so using the latest digital technologies to link things together, supply chain, you know, artificial intelligence to actually make the processes more efficient in terms of energy use and other things as well. So the project itself started with the core of Sheffield, Swansea and Warwick. So Swansea's what we call the hub, and Warwick and Sheffield are the spokes. And as the project's grown, we've increased. So Durham University is, so Andrew Gallant, who's giving a presentation in the future, him and Alton Hosfeld have been developing some high temperature technology for measurement in steel. They've got up to 700 degrees without water cooling, no power, so it's an RFID type system, and they're working on a technology that will actually provide a similar sort of sensing at up to 2,000 degrees without it damaging the electronic components. So it's quite novel technology, because steel's one of the industries where, you know, it's so hot that you know, you can't use the same measurement and analysis techniques that you can in other sort of chemical-based industries. So that'll be a big gain. Plus the digitization that we're bringing as well. It'll bring some really big benefits. So as well as as Cardiff and UCL are also involved. Cardiff are providing, they're working with Peter Holloman at Swansea, and they're looking at reuse of plastics and wastes as a substitute for coal in the blast furnaces, and also in the arc furnace as well, because it's part of the process to treat the slag. You need to add carbon, and it gives this like sort of a boiling effect that causes insulation and also gets some of the nasties out of the steel and the inclusions. And UCL are looking at the supply chain side of things. So as well as the core there, we've got, as I mentioned, the steel companies, and we're also working with other institutes as well, such as MPI, you know, the high value manufacturing catapult, Warwick Manufacturing Group, part of Warwick, MTC, EMRC, the Royce Institute, and we have UK Steel involved as well, who do a lot of lobbying to try and you know, get the policy and conditions right to allow UK Steel to flourish. So Sustain itself split into these different projects. So we have our, as we call our grand challenges, so carbon neutral iron and steel making and smart steel processing. So within the first one, we've got the emissions management and utilisation, and we've got this emissions control project that I'll go into detail, and that's primarily about providing a means for capturing the CO2 out of the flue from the blast furnace and the Boss plant, and also the mills as well, and the arc furnace. And as you can imagine, it's not very clean. It comes out with lots of contaminants, and those contaminants can damage the capture system and the catalysts. So we've got to do something about that. So it's quite a, it's not as simple as it is in some other industries. Yeah, again, you know, steel's hard. It's difficult. And we're also looking at doing conversion of that CO2 into not just pharmaceuticals, things like that. It's also sort of feedstocks. I'm not sure if I'd want to eat it, but you know, I'm sure it's fine. Some proteins, things like that, dyes, and you know, fuels, things we can reuse. And the idea is if you can keep that cycle going, so you basically you get a second bite of the cherry, and then if you're using it as a fuel, you then do some sort of carbon capture and storage or carbon capture and utilisation to bring it back into circulation. And then our second theme, zero waste steel making. So we've got a waste reprocessing project that I mentioned earlier with the Cardiff and Peter Holloman, and that's about basically substituting the coal that you would have in the steel making process for the carbon from plastics. We've got a big project on scrap utilisation, and that's augmented by some of the work that I'm doing. We're hoping to build a national centre in the UK, be a world first for scrap processing. Because what tends to happen with scrap is it gets what we call downcycled. So you take some scrap from a car body, it never ends up back in a car body again. It usually ends up in rebar or you know, something of a lower grade, and that's a big problem, particularly because most of the scrap we produce is from, you know, automotive white goods, things like that, stuff that's very close to being pure iron. And what we really don't want to do is contaminate it, and then it go around the cycle again. Then there's only so many times it can go around the cycle before you basically need to landfill it because it's of no use to anyone. One of the big problems that we have is copper. So as you imagine, most of the automotive and even white goods now, you've got so much electronics in there, and you know, got so much copper in there. And when the scrap guys, you know, when you put your washing machine out or into the yard and they pick it up, it never gets segregated initially. They basically just they do to some sense, but what happens is you end up with a soup of lots of different things all mixed up together, and it contains large amounts of copper and other elements as well. And when it goes in the furnace, it's locked into the steel, very difficult to get out. It's not economically feasible to do it. We also have one on novel reductants as well, which is one of the new tasks we've brought in. And then we've got our third theme, which is data-driven innovation. And this is split into two aspects. The first one is about using digitization for supply chain, and also looking at technologies like blockchain. So you've heard of Bitcoin, so it's a fully encrypted way of actually having a ledger of different conditions within steel. So you'd be able to know where the raw materials came from, where it was produced, how much energy it took to make it, what the CO2 was, and then have a unique identifier, possibly from the steel itself. So you could chop a slab up into a million pieces, and then you'd be able to basically you have a certificate, digital certificate that you could only actually unlock if you had that, you know, unique sort of identifier, unique fingerprint for that slab. So you know, things like that would stop imports from countries who didn't care about where they got the raw materials from, or you know, we're using blast furnaces and weren't using carbon capture and storage, that sort of thing. So it gives an extra value to the steel, and then it allows government to use policy effectively. And then we've got this task 5, intelligent steel making, and that's about making effectively what we call like a digital twin of the steel plant. So you can basically model all of the expected outcomes from a process and control the trajectory of the actual process itself without having to measure everything. It's very difficult to measure in some aspects of steel making. You can't measure, you know, every second or every millisecond like you can in other industries. So that sort of fills some of the gaps up, and it'll also allow things to happen like you can predict how the steel's going to perform if it's slightly out of its range in terms of the additions and the you know, the final product quality, and you'll be able to determine before it goes to down the supply chain exactly how it's going to perform. You'd know whether to downgrade it or to you know, whether it was going to actually work in the area that it's supposed to work. So moving on from that, I'll have to speed up because I want to get on to the interesting stuff. We've got this theme 4, which is smart low energy production, and that we've got task 6, which is about thermal efficiency. It's basically focusing on refractories, and the Swansea team looking at that are also looking at ways of actually harvesting the heat that comes from the ladles. It's very difficult to measure to recover heat from ladles because they move about. It's very difficult to, you know, have a system around it that can absorb the heat and sort of produce electricity or you know, change the energy to something else from heat. And this allows it's a refractory material that's effectively like a thermopile, so it'll produce an electrical current and voltage based on a temperature difference. And it's based on refractories rather than metals. Then we've got this disruptive processes. We're looking at hydrogen DRI. There's still issues with producing DRI, directly reduced iron, through using hydrogen rather than natural gas. And we also have big issues in where we're going to get this hydrogen from. One of the UK foundation industries recently used they did a trial where basically they powered one of their furnaces with hydrogen for a week or 2 weeks, and they used up all the hydrogen in the country. And that's just one industry. It was the glass industry. So you can imagine we've got major problems there. And then a lot of these companies that produce the hydrogen make it from natural gas, invent the CO2, so you're getting, you know, less energy in effect, and for the same amount of CO2, you might as well just use the natural gas. Task 12 is the Thermos project, which is the Durham one that I mentioned. I thought it's quite a good name for that, Thermos, for an electronic device that basically doesn't melt when you put it near liquid steel. And then we've got the last tasks here. So task 8 is about, you know, sensor technologies, and that's looking at using electromagnetic systems to determine basically the grains of the steel in real time as it comes off the caster, so you know exactly what you're producing. You can tweak the system rather than just have a model and then just run it, and if it doesn't work, you change the model. So it's reducing wastage, giving more feedback. And then late stage product definition and integration. That's based on the concept of, do we really need to keep adding all these alloying elements to the steel? Can we not just use thermal and mechanical processing to get the same properties? And then the last task 11, UHTRED. That one is based on it's a supply chain type model, and that's the one that's been performed by UCL. So just to quickly say, you know, where Sustain sits. So I think everybody's probably aware of what TRL levels are. So it was developed by NASA. So TRL1 was Kennedy saying we're going to go to the moon, and then 9 was, you know, they got the moon and back. So it's that sort of model. And we are based in the sort of the low TRL, the bright ideas, and then our model of operation is, once we've developed them to a stage where we're confident in them, we then go for other funding within the UK, such as you know, Innovate UK, some of their programs that they have, and that allows us to then pilot them, do the upscale, and then the industries can then take them on from that. But the commercialization side of things is it's probably the most difficult part. You could have an idea that, you know, seems to work in principle, but actually getting it to work in practice in a real plant is something else again. So what our motto is you know, steel's not a problem. So steel's got this Dickensian connotation to it, and it's seen as a big problem. Let's just shut all the plants, because if we do that, then we'll get rid of the CO2. We say, you know, steel's a solution, not a problem, and it can be part of a solution to decarbonisation and the you know, the climate crisis and everything. by basically valorising the internal waste, reprocessing external byproducts, and you can see the list of the projects here, becoming decarbonisation hubs, increasing scrap recycling, and we're going to provide a solid base to build a smart steel future by integrating conventional modelling and data science, game-changing sensing technologies, and novel metallurgical processing. So, we see ourselves as being potentially a solution to a lot of the problems that we have in the UK at the moment. This is just a quick slide to show, how we're doing as a project. The slides will be shared. You can read through those later. And another list of the projects there. So now I'll start with some of the interesting stuff. So T1, Task 1, this is the Carbon Conversion Environmental Pollution Project. So that's been led by Andrew Barron and Enrico Andrioli at Swansea and Peter Styring at Sheffield. And basically, the whole point of this is, can we sequester the carbon dioxide, use the carbon embedded within the carbon dioxide for other things. So it's a two-step process. You need to get it out safely. You need to make sure that you get rid of the nasties, and then you can start doing something clever with it. And there are various technologies that are being used at the moment, such as amine technology, which aren't suitable for steel making because of temperature and pressure swing, things like that. And then the nasties in there can damage the catalysts that do the clever stuff with the material as well. And then we then need to find either bio or electrochemical ways of producing the useful products to replace things that we currently use carbon from oil for. So basically take the carbon dioxide from the steel industry and then turn that into fuel and chemicals. And the great thing about steel is it's a fantastic point source. You do see, or you hear in the papers about companies who are taking carbon dioxide from the air. So, there's a very small percentage of carbon dioxide in the air. I think 400 parts per million we are at the moment. Wouldn't it be much better to go straight to the source and just, suck it all out where you've got a very high percentage of carbon dioxide rather than wait for it to get into the air, diffuse, and then try and pull it out. So that's what we're really going for. And in the UK, we've only got two, unfortunately, integrated steel plants now. So we've got Scunthorpe, it's now British Steel, owned by Jingye, Chinese company. And we've got Port Talbot, which is Tata Steel, owned by an Indian company. But still going, still in the UK, we're still making steel. So we've got two sources that we can stick these systems on, and we can start to prove to the world that you can actually have integrated steel making and use the byproducts for useful things rather than letting them go into the air and vent off. So the aims and impact of the first part of the project, it's development and build and operate a pressure temperature swing absorption units with purposely designed absorbents, higher CO2 separation selectivity, low energy potential, and deliver separation units and absorption materials for efficient carbon dioxide capture from gas mixtures specific to steel making. So this project's been going for a couple of years now, and it's reaching its maturity. So it's getting to the point now where it's either going to be spun out through an Innovate project or given directly to industry. The technology that's used, so initially they started with electrical conversion of CO2 to ethylene using a catalyst process, and that was proven to be very successful. It's the energy used is far less than a lot of the other processes that are currently used today or in research today as well. And then they were also looking at bioreactors as well. So you basically have a big tank full of algae and you pump the CO2 in and they're converted into various things that you can then refine and make into useful products. So where this is now, the capture side, the non-amine based technology is actually suitable for variable pressure, and it's going really well. They're actually at a stage now where they're building it should be finished in the next few weeks, a demonstrator, and that'll be doing a tour of the UK. It'll be going around different plants, different steel plants. They're actually going to go outside of Westminster and pull out of the air as well, just for giggles. But it's at a point where we can really start to get the message out, get the investment into the project, and start to scale it up. But the actual proven side of it's pretty much finished. And then in the utilisation side of it, there's a successful setup. I mentioned about the ethylene production through the catalyst, so that's been proven. And then we've got this other system with the algae. There's a bioreactor's been set up in Valais, it's a nickel refinery in South Wales. And yet again, it could be put on skids and be moved about. And that's going to do a tour of some of the steel plants as well. We hope to put both of the units together as a full demo, and then take it from there. So this is a system that'll take the CO2 out of the blast furnace or the mills or the Boss plant or wherever, and actually before your very eyes, it'll convert it into something that's useful and can be used. But like I said, I'm not sure if I would eat the protein that they make from the algae. So the second project I want to talk about, so this one's yet again it's a Sheffield Swansea project. So the two researchers are Ulrich Jones and Fazwaz Ojabali, with Richard Thackeray as the primary investigator at Sheffield and Peter Holloman at Swansea. So what they're looking at is, can you use plastic waste basically in some sort of process form? It's actually plastic and paper, the type of material that they're using, a bit of a mix. So it's stuff that would end up in landfill, stuff that we throw out probably every day within the green wheelie bins or whatever, or the blue ones, whichever system we have. Basically that needs to be processed into a way that mimics the way that the coal goes into the blast furnace. So I don't know if I'm assuming everyone here knows how sort of a blast furnace roughly works, but you do need to give additional fuel to it, and they usually use pulverized coal, and that's put through what they call a tuya. And this is a project where, on a lab-based scale, they've been simulating the tuya and looking at how basically the carbon burns and the differences between the pulverized coal and the stuff that they're producing from plastics and paper. And the idea is that there'll be potential financial savings. So landfill of this stuff's like £120 a tonne. So effectively you're getting like a saving of whatever the cost of coal is for an equivalent of plastic, plus that £120 a tonne that you would normally pay for landfill. So it's there's a financial saving, but also a carbon saving. So if you then combine this with the previous technology, then you've got something where you've got the second bite of the cherry from the plastics and the paper, and then you've also got that ability to pull the carbon out and then reuse it again as something else, as a protein, or you could even make plastic again out of it. And the idea is you'd have that efficient cycle. You won't have to keep using oil, and you won't have to keep getting virgin materials and putting it through the process. So next project, it's wholly a Warwick one in terms of the practical side, and then Richard from Sheffield's working on that from a LCA analysis, that's life cycle analysis side. So he's looking at, instead of, usually today, like with cars, there's been, for many years, they've been doing the life cycle, and that's where the weight of the cars come down by alloying the steel in a certain way to give it higher strength, so you can have thinner steel, the same ductility, and then actually reduce the amount of carbon dioxide that's put in the atmosphere by the reduced weight of the car. And what Richard's doing is rather than look at one life cycle of a vehicle, he's looking at sort of an infinite life cycle. So that starts to bring questions in, well, if you then got to recycle it and it becomes more difficult to recycle because you've got these alloying elements in, you could get to a point where you've got a negative gain. So this is all integral to looking at the far future rather than just the next 5, 7, 12 years. So there's the scrap project at Warwick. As I said, I'm doing some of the things on scrap as well. But the main thing is to look at the UK generated steel scrap and actually use it in a way that's strategic for the UK. As I'll come on to later on, we actually have a surplus of scrap in comparison to the amount of steel we make. Unfortunately, we still use more steel than we accumulate scrap every year by a factor of about 2. So we've got that will start to level out. The amount of steel we use will come down, and the amount of scrap we basically generate every year will go up, and it'll meet at some point. And until we do meet that point, we then still need to have some form of virgin iron ore to top things up. So then we start looking at carbon capture and storage for blast furnaces. Blast furnace is the most efficient way of producing iron, but then there are other technologies as well, like the hydrogen DRI, gas DRI. There's some of the new technologies coming up as well, using electrolysis and sort of leaching, things like that. So, you know, there's various things we can use, but as I say, we're in a state now where we need to start thinking about where we do go in the future and what that transition plan's going to be. So basically, we need to ensure that the scrap that we use is segregated. We need to start looking at things like, can we reuse things rather than basically just melt it all down and you know, lower the usage of it through the properties degrading if you're getting entrainment of other materials or you're getting mixing of different steel grades. The project's really just looking at that, that ground level, and also looking at how much we can tolerate. So how much copper can we really tolerate? Can we use different casting methods? Because one of the problems of copper is it becomes much more harder to cast if you've got a high amount of copper in the steel, because it ends up going to the grain boundaries. You imagine copper's got much lower melting temperature. When you cast steel, it goes through a curved caster. When it curves, it cracks open those liquid boundaries, the steel comes out. And you can imagine the steel doesn't actually become solid until, you know, 20 odd meters down the caster. So if that happens, it's say, you know, 15 meters through, you then have, you know, 15 meters high caster, 15 meters ahead of steel, and the steel just squirts out. It costs the steel company about £250,000 to £350,000 every time that happens, because they've got to repair, they've got to shut down, they've got to, you know, stop production, that sort of thing. So, you know, there's various different ways we can change the casting technology to overcome that, and then we've got to look at how it affects the end product. So I don't know if anybody knows how tin cans are made. Basically, they get a sliver of steel, like a beer mat, and then it's punched out into shape in one go. If you have too much copper in there, it hardens the steel, stops it being as ductile in certain areas, and then you get cracks and splits and tears. And they want like 1 in 10,000 to, if 1 in 10,000 rips, that's okay, but if every 3 rip or every 1 rips, then you've got, you know, major problems, and they'll just send the steel back. So basically, I've gone through these. The T6, which is Cameron's project, there's a floating head there. So that's Professor Cameron Pladle. He's working on this project that's looking at extending the life of the refractories. So refractories are really important for steel making. We use iron or steel ladles. Steel making vessels are made of steel. So you need to have some form of refractory material within that to actually reduce the amount of temperature or heat that actually gets to the outer shell, so we don't melt, you know, the things that we make them in. Very important. It can be quite expensive because you've got to keep renewing these refractories. He's looking at not only generating the electrical energy from the heat, but also looking at how we can extend the lifetime of refractories as well. And yet again, refractories, it comes from virgin materials that are dug out of the ground. So, you know, can we find some way to reuse them? Usually what happens with them is they may be mixed up with some of the slag and then used in, you know, to make sort of tarmac for the roads, that sort of thing, like road surfaces, or it's landfilled. So yet again, it's another waste. We're digging something up, we're using it, we're consuming it, and we're throwing it away again. So that's just a picture of the thermopile, the refractory thermopile that would be installed within the refractories of a ladle, and then obviously you generate from the temperature difference, you generate a voltage, and if you have enough of them stuck together, you get a parallel sort of current from that increases the current. So it's basically I'm trying to think of the word now. Oh. It's gone. Anyway, you know, like temperature measurement system where you've got two metals, sort of two metals. Thermocouple, that's the one. Yes, thermocouple. Anyway, so moving on, disruptive technology. So I've mentioned this a little bit, but this is getting into the hydrogen DRI side of things. So there's a lot of research going on into producing direct reduced iron from iron ore using hydrogen. So effectively what you need to do is reduce the iron ore, take the oxygen out, and leave you with pure iron, or close as pure iron. And you do that either using the carbon within or carbon monoxide that comes from the gas, the natural gas at high temperature, or hydrogen. It'll take it out and obviously form water, but at a certain temperature. There's a lot of problems with the hydrogen-based technologies. One of them is actually getting the supply of hydrogen, especially if you're not going to be using the natural gas to do it, which is wasteful. You can do it through electrolysis, but it's roughly 60% efficient, so you're losing 40% of the electricity that you're putting in there. You might as well use electricity and melt scrap if you're going to do that. So there's that side of things, but also hydrogen behaves differently to natural gas. And then you've got a lot more water formation within there, which can cause problems as well. So Zushu's got a PhD looking into that at the moment, and we're linking up with world leaders who are really looking into the uses of hydrogen for DRI, that sort of thing, and trying to learn as much as we can about it and bring the knowledge into the UK. And then we've also got the other project, which is looking at different forms of casting that can be more efficient energy-wise, but also overcome problems that you might have with traditional casting methods in terms of casting highly alloyed metals due to residuals from contamination from recycling. And then the last one I'm going to quickly talk about is this late-stage differentiation and integration. So this is a wholly Sheffield project in terms of the practical side, and then there's a PhD working at Warwick with Martin Strangwood. Mark Rainforth there, really good guy. He's a world leader in this sort of thing. Does a lot of work in sort of for the nuclear industry, that sort of thing. And one of the spin-outs of this project actually going into the Neuron project, which is looking at nuclear fusion. And Eric Palmier, yeah, again, he's another world expert based at Sheffield. So it's all about improving product uniformity along length and cross sections, microstructural evolution during hot deformation, novel innovative heat treatment to reduce heat treatment costs with and without alloy design. What's happened over the years is we've gone away from the mechanical and heat treatment and actually, I wouldn't say cheated, but we've put what we call microalloys in there that actually give you the properties you want without having to invest in roller mills and heat treatment. So it was something that British Steel really pushed when it was British Steel back in the good old days before it was Chorus and then Tata. As a cost-saving measure, it was a short-term win, but long-term it hasn't really benefited the company, I don't think. And looking to the future, looking to recycling, it's definitely not the right model because we're increasing the amount of contamination within the steel that we need to recycle. And the last one there, increased potential for recycling. So if you can control through heat treatment and rolling the grain size and the properties of the steel, then you don't need to add all these elements, and you don't have the problems you would have otherwise with these alloying elements that you put in for the recycling. So steel is a solution. I've covered some of these things already, but plastics, we can use plastics and paper as fuel. We can couple that with carbon capture and storage utilization to minimize emissions. Something we're really focusing on in sustain. And then we've got greater utilization of steel as packaging material. Something we're really promoting because steel's so versatile and so recyclable. Why would you use things like plastic? The cost is potentially lower. You can get steels to a really thin sort of state that's going to it's going to be light. It's going to be it's going to be useful. I think we've seen that a lot more. There's a lot more packaging now. I've seen cans of water on the shelves and things, and just moving away from that overuse of plastic. I don't think we'll have steel carrier bags, but I don't know what we're going to do with carrier bags because they just seem to be everywhere, don't they? But as I say, I think steel itself can have a massive impact on the plastic crisis that Attenborough sort of brought forward a few years ago. Because if you look at the if you look at the state of the streets, you look at some of these pictures of like quite exotic locations and the Arctic and stuff, and it's absolutely it's covered in plastic. It's destroying marine life. Some of these plastics break down into nasty chemicals and that mimic hormones and are causing issues not just in wildlife but in human beings as well. So the circular economy. Recycling versus mining, transport, virgin steel production. So, if we really look into the decarbonisation side of things, if we can use our own natural resources that we have in terms of the scrap and the waste, we don't need to start bringing all these virgin materials right the way across the globe. We get our iron ore from Australia, coal from Australia and various other places. What's the carbon impact of that? I didn't think it was controversial, but a lot of people, I was on the side of that Cumbria mine opening because, it's bringing jobs, it's less transport, and all, as you saw on that graph earlier, all we're really doing is we're actually putting the burden on other countries, and we're saying, oh, what a good job we're doing. We're still using the same amount of carbon, so why not use our own natural resource? And obviously, I come from a coal mining background. Grandfathers were coal miners at Horden Colliery. If we do it right and we capture the carbon at the end of it, is that so bad? It's better than all of the the stages of digging out of the ground, transport. When it's dug out of the ground in some of the third world countries as well, I'm not sure if that's the correct term anymore, but you don't know what the conditions are. You could have child labour, you could have all sorts of things going on. At least it's under control, health and safety is right, the transport costs are really low, and we're using our own sovereign capability. And if you look at what's happened after COVID, that much reliance on China for things, we need to start bringing things back into the country, because if they switch the lights off, we can't switch them back on again. So, yep, carbon capture and reuse. So, oil industry, it's on it's a really negative now. It's on its last legs. Not because we're running out of oil, but because it's public opinion's shifted against it. All you can see is a decline and increase. You can see the fuel prices going up, and it's going to be crazy. We need to start really looking at what we have at home and how we can actually reuse that and use that for practical means. And then hydrogen economy. One of the really interesting things about the blast furnace is you can actually use a blast furnace to generate hydrogen. So one of the things that Tata Steel was involved with and we were really championing was actually using the CWEGS process, which effectively you can turn the CO2, you can react that with steam, and you can actually produce hydrogen. So you could, I think the calculation was something like 350 megawatts or something, I think it was, 300 megawatts of hydrogen for large blast furnace. And then if you compare that to the Fukushima Hydrogen Energy Research Centre, it was 180,000 metre square site, cost them $2 billion, and they get 10 megawatt hour H2 output, which I think powers about 60 cars. So, just an investment of what? Just an investment of $500 million, and then you've got, orders of magnitude more hydrogen, and we've already got the blast furnaces. Why don't we utilise them for that? Kickstart the hydrogen economy, rather than wasting money on renewables that aren't maybe as developed as they need to be. And then you've got to think as well, why not just use the electricity? Because 60% of it is going to be used to produce the hydrogen. The other 40% is lost. So it's to me it's a no-brainer. But as I say, it's quite difficult to convince people it's the right way forward. And then steel for nuclear fusion. So that's the new thing. Was it 2070? They said we might have a reactor that lasts 5 minutes or something like that. They've proved it lasts so many seconds. And obviously fission as well. This is another one that people hold their heads at when I mention it, but we've got an opportunity to use these small modular reactors. And to produce them, we need to have steel. So steel could be a solution for that. We've roughly got about 500 years of energy from depleted uranium. That could be enough to get us, to the next stage. And I really do think we're going the wrong way in terms of shutting the lights out with fossil fuels well before we actually we're at the point with renewables that we can actually really use them, rely on them, and produce them with an amount of energy that's you know, significantly less than it takes to produce the things in the first place. So, future for the northeast of England. It's been quite dire. I mean, if you think back, there was steel plants at Hartlepool, Concert, Teesside, obviously, and I was involved with you know, when they tried to relaunch Teesside as SSI, and it was quite sad to see how that went in the end. They would probably still be here if it wasn't for the steel crisis in 2016 that was caused by dumping. It was quite a sorry thing. They had a really good business model, but it's all gone now, and you know, we really need to start from scratch if we want to bring it back. And I think to do that, you know, we need to start looking again at the UK. So we've got a wealth of low quality virgin ores in the UK. So the Cleveland Hills, it's still, you know, full of iron ore. It's not the same quality as the stuff you would buy from Australia or elsewhere in the world. It's got high phosphorus. I don't think the actual iron levels as high as, you know, the premium iron ores that you would get from Australia. But it's somewhere to start, and there are technologies that have been developed that actually, you know, use that and you know, take things forward. We've got a surplus of end-of-life steel scrap. So as I mentioned before, it's roughly 10.3 million tonnes of scrap generated every year in the UK. We only produce 7.2 at the moment, which is sad because it was, you know, 21 million tonnes, 27 million tonnes, I think, in the 70s the UK used to produce. So, you know, we're really, you know, right at the bottom end. But that might be a good thing because it's better to build up than to scale down. So I think, yeah, again, the UK is in quite a good position. And I think we also, in the UK, we seem to be very good at innovation and coming up with new ideas. And, you know, when our backs are at the walls, we always seem to sort of, you know, turn true. So I think we've got that going for us. And we need to start thinking about new business models as well. Because I think if we go to the circular economy from the linear economy, we're not necessarily going to be making steel at the same rates as we did before. Economy of scale is not going to, it's not going to, we're not going to be able to use that for low prices. Steel might be more expensive, but you know, we do need steel to keep the lifestyles that we've all been brought up to expect. And I think you know, going back to the Victorian times or you know, the Tudor times, it's not going to really turn many people on, really, is it? So one of the things I've been looking at is these different technologies and where they are in the technology readiness level. So a lot of the technologies are quite low down in the TRLs, just beyond sort of concept to pilot. The one that's at the highest level, so the closest to actually being realised, is to maximise the scrap usage. So that's somewhere where I think we need to really focus. And if you look, this is just yet again from the World Steel Organization, and you can see all of the different you know, amounts of steel that are exported, imported, and the amount of tons that are produced in different countries. And you can see the United Kingdom there. We've got, oh, press wrong button, sorry. So United Kingdom there, 7.2 million tons produced. And if we look, you know, we've got the amount of scrap that we export, and obviously we do use the scrap within the UK as well, and we do import some as well. And as I say, the number comes to about 10.2, 10.3 million tons. So, but even that number there is higher than the number that we produce. So why don't we use our scrap as a UK sovereign resource? So there's a summary of what I've just said. We export that 8.1 million tons, bring 0.3 in. Our actual use is 21 million tons. So as I said, we are going to have to bring up the amount of virgin iron that we use. But it's, you know, it's definitely something that we can use to kickstart and reinvigorate the steel industry. And it's also a much cheaper, much more green way of producing steel if we can use arc furnaces, or even if we can start using more steel, more scrap steel within the blast furnace. So you can actually use up to, I think, maximum of 20% has been trialled of scrap steel within a blast furnace, and about 30-35% in the Boss plant. So when you add all of that up, it increases productivity. You don't need to have as much carbon added to the blast furnace because the scrap's already reduced. So, you know, it's got other benefits as well. So you can start reducing the amount of carbon that you consume, but also increase productivity as well. So what's wrong with scrap at the moment? It's under-processed, and it promotes this material downcycling that I mentioned. So at the moment, you can't really use 100% scrap to make car body parts or tin cans or the premium steel products. So the chemical composition of the steel scrap needs to be measured. We need to start either segregating at the source or having much more vigorous separation processes for the scrap that we get in. I think eventually, all sort of industries you'll have with cars, it'll be, your Jaguar Land Rovers or your Nissans will buy the cars back and then, shred them up, and then it'll be, it'll be separated after that and sort of disassembled, and then you'll know exactly what you're getting back in terms of the metals that have been used in the vehicle. But we're so far away from that at the moment. The design of cars and various consumer goods are all basically for assembly, not for disassembly. So I think that's going to take time to get us there. And then also, the use of very similar type materials using heat treatment rather than alloys will start to bring the steel grids into much less. I mean, was it the number that I put up at the beginning? Since 2000, over the last 20 years, we've got thousands of different grades of steel. Let's have 5, let's have 10, something like that, where you can actually segregate it. You're not really going to be able to segregate 2,000 different grades of steel. So we need to start to pull things together for that. The processing of metallic waste is critical to the future domestic sustainability. So not just steel, so using the economy of scale of steel, using that 10.3 million tonnes, actually start to use that to separate other materials like the copper, technology critical elements for your touch screens, your indium, your platinums, and the things that use in the catalytic converters and in the batteries and the LVs. We can actually use the economy of scale of steel processing to bring down the cost of processing those things as well, separating them, and then we've got our raw materials for remanufacture within the UK to start to kickstart things off again. First step in achieving UK material sustainability is to extract a high purity Fe secondary raw material. So once we do that, we can start using 100% scrap to produce new steel products. It's going to remove the volatility from the melting cycle. What tends to happen at the moment, you buy scrap at a premium grade of scrap for a steel plant, and you think you're buying 98% Fe, and it's actually something like 86, and the rest of it's plastic, glass, soil, lots of soil, water. It's all sort of added up. Anything the scrap man can put in there and hide gets put in. So what happens to that? It ends up in the slag, or it ends up in the steel itself. It ends up in the slag. It bulks the slag. That's more landfill, more cost. So it's all, it all adds up, and it all adds up with the overall profitability of the product in the end of the day. So just to give you an idea of what the scrap man shows, so these are a range of grades, a scrap menu that you get from, this isn't just the UK, this is global. And you can see, the percentages there. So 92% for the OA grade, which sells at a premium, right the way down to the carbon steel turns, which is only 70% Fe. And then the rest's, oil, soil, other things that are hidden in there as well. And what the scrap companies will tell the steel plants is that's the best you can get. You can't go any better than this percentage here. In fact, most of the steel companies think they're buying 98% Fe, and they're not. But if you do a quick calculation on the available steel, that's the globally available steel, 70% is made in a blast furnace, and the only reason it has the 0.05% copper in is because you add scrap within the Bosch process as a coolant, up to about 15% at the moment, and that has copper in it that gets diluted down. If it's any more than about 0.152%, 0.2%, then it becomes useless for making high-end grades for automotive, things like that. But that level of copper there could actually be much lower if we're putting the steel in from a purer source. So once you've actually started to separate all of the contaminants out, when it's been reused in the recycling, when it's recycled back round again, that level should drop much lower. But I'm getting off the point. If you do a sum of those percentages for the different types of steel, that go to the different plants, the EAF and BOS. The total that you should actually get is 0.125%. And then if we look here for copper, so CU, second column there, you know, the best you can really get. I mean, you get 0.03 from the loose cuttings, 0.05 from cast iron, but some of those premium grades, you're talking 0.2, 0.35, 0.38. It's you know, it's nowhere near where it needs to be, and you can't make the high-end products with that. So it goes from this to that if you do processing and extra processing, and it's just a matter of making sure that you do segregation, that you actually you shred it up into very small pieces, so you get the separation of, like, if something's bolted on, or you know, if something's connected, welded, or brazed. So if you cut it up into small enough pieces, all these things drop away, and you get less contamination. And we need to ensure that we have adequate analysis. None of the steel plants or scrapyards do any analysis on the product as it's going through, so they've got no control. So the scrap that ends up going to steel plants ends up being quite variable. So what we need to do is take that 10.3 million tonnes and actually process it correctly. And what we should have is the right type of steel, so the very low, the high purity, very low residual steels for your high quality strip. And then, you know, obviously it doesn't need to be as pure for your commodity strip. Your specialty grades come next. Then you've got your long products, your commodity long products, and your rebar at the bottom. So rebar can have up to 0.7% copper, and that's just the stuff that they put in the concrete for buildings. But we've got enough steel to go around for everyone. And we need to ensure that all of the UK's steel plants actually buy the right type of scrap for the product that they make. And if they do that, there won't end up being a massive bidding war on scrap. Because at the moment, as you saw on the previous slide, 70% of the steel that's produced in the world comes from the blast furnace. That leaves only 30% for everybody. So if everybody switches to arc furnace, there's going to be a massive drive for everybody to buy the scrap, and it's going to go through the roof. So, you know, we do always still need to have that virgin supply of iron. So back to the UK and Teesside. So, you know, UK mining ceased due to low quality of ores, not exhaustion. So we still do have our own natural resources there. There's still a significant amount. It's lowish in Fe, high phosphorus in comparison, but there are technologies that can deal with that. And then, you know, it's all about this sovereign control and bringing control back to the UK, not just for the foundation industries, but also for manufacturing. So these are a couple of examples. So there's Boston Metals. It's an American company. They're looking at electrolysis. So rather than actually using a blast furnace or a arc furnace or you know, producing HBI through an HBI furnace, they use an electrolysis process, and it obviously just uses electricity, and they've shown some really promising results from that. Then we've got a technology that was developed by Tata Steel. It was called Hysana, which can actually cope with the low Fe and the high phosphorus in a way that the blast furnace can't. And there are other methods, various catalytic leaching methods. You don't necessarily have to use carbon as a reductant. You can maybe use, you know, some other elements to do that as well, and that needs some research. But all the suitable processing routes for these low quality ores, and all these methods are scalable. Are these scalable to industrial volumes? We're not sure. Hysana was trialled in the Netherlands, Tata Steel in IJmuiden, and it's now onto a second stage where they're going to build a semi-production scale one in India. And if that works, then, you know, that could be rolled out within the UK and IJmuiden as an alternative to blast furnace. It also has a much lower carbon dioxide output, and then of course you can use your carbon capture and storage to add to that. But what I think would be a good idea is to use one of these small modular nuclear reactors and arc furnaces. So if we can process the scrap to the level that we need to get it, we will still probably need to top up with a little bit of iron, you know, from HBI or something like that. But what we could do is basically get a Trident submarine, take the power supply out because they last for 50 years, and the safest houses, people have, you know, lived in these submarines for years without any problems. It's an all self-contained unit. The government is trying to convince people to take on, you know, trials using them. Obviously, it's very expensive. There'll be some subsidies to get them out there, but I'd like to see this, you know, maybe it's in Teesside or even in South Wales or wherever. But having that actually power the arc furnaces, so we're not relying on the generic electricity supply that is dwindling and fluctuates because of the renewables, the wind power, photovoltaics, and a bit of natural gas that we do and a bit of nuclear. So you've got your own sustainable power supply. That could be used for hydrogen electrolysis as well, so there'll be energy to spare. You could then use that to power your DRI plant or your HBI plant, and you could also use it to charge kickstart the UK hydrogen economy as well. So, you know, something like that where you're actually, you know, using a lot of recycled material. You'd use your hydrocarbon wastes for your DRI plant as well. You could also use it, you know, for you know, the gases that come off to produce your substitute for petrochemicals. And one of the benefits of doing this as well is all of the copper, the gold, the tin, platinum, indium and everything that gets mushed up in all of the scrap. If you can separate it out, you can sell it, and it's obviously got a much higher value than what the steel has. So you've got another method there for kickstarting different elements of the UK supply chain. So, is the linear economy business model applicable for the future? No. So I've drawn some lines through that, strike them out. You know, low cost, high volume production, consume and dispose, mixed, contaminated scrap reuse, downcycle and scrap. That's not the way to go. Circular economy, so localized manufacturing refurbishment, byproduct recycling hub. So that's something that we put a paper into this Teesside regeneration thing that's ongoing at the moment with Ben Hoogan's sort of leading, and that was to maybe, you know, start up a hub within Teesside where you've got not a massive steel plant, but what we call a micro mill. So you're actually just producing a small amount of steel, and within this larger hub, you've got your manufacturing components and refurbishment plants. So let's take automotive as an example. So you've got Nissan up the road. Let's say somebody's Nissan car's a bit worse for wear, needs some new parts or whatever. You know, they come back there for all the parts come back for refurbishment or recycling if you can't refurbish them. And the stuff that can't be refurbished goes through the micro mill, produced into new steel. You minimise the amount of steel grades that you have, so therefore, you know, it's much easier to produce the different components. It's all done on demand. It will be much more expensive, but you know, the long-term possibilities are better. And effectively, over time, you'll have you know, millions of tons of steel in circulation from it could even be a 40,000 ton per year plant, very small, but it's always in circulation. It's always owned by, it could be owned by the steel company or the car company, or, you know, or shared throughout the hub, where you have all of the support elements in there as well, and you've effectively got a localized system for you know, for providing the services that we need. You know, it could be stuff like white goods, yellow goods, you know, whatever, tin cans. But as I say, having these different hubs in local locations where it's not supplying to everybody in the country and the world, but just locally, I think that's you know, it's an interesting model. I don't know if it would be successful or not, but that's one of the things that we're looking into. And I think you know, focusing upon longevity and refurbishment rather than disposal, and you know, we require practical source and process validation and tracking. So one of the projects within Sustain is looking at blockchain, as I mentioned. So you know, you'd be able to track every single piece of steel. You'd know what was in it. You know how it was made. You know how many times it had been around the cycle. That sort of methodology. And why the Northeast? So logistics. You know, it's highly developed, high volume. We've got fantastic access, road, rail, and sea transport, raw materials and product transport. We might need to initially outsource some of these manufacturing capabilities that we don't have ourselves, but we have the raw materials, you know, so rather than having to be reliant on another country to supply lithium or you know, indium or other materials, we'd have it at hand, and we just basically, we'd use that as part of a barter to get things made much more cheaply. Energy, we've got a fantastic energy source here. There's the off-grid electrical network at Teesside as well. Carbon capture and storage, everything's going to be sort of close proximity to the North Sea oil fields if we want to actually do the storage side. I'm not a big fan of that. I'd rather, you know, see if we could reuse it and use it for producing new chemicals. And then you know, we've got the knowledge. Teesside, we've got a long history in steel making. It is quickly diminishing though, but there's still very knowledgeable people within the area who know a lot about steel making, who could be brought into such a project. We've got a lot of excellent engineers and people with various skills that can make this thing happen. And I think that across the country it's been lost. Teesside we do still have, and sort of the northeast in general, we do still have a lot of those skills. So government funded entities like Sustain, we've been active in sort of recruiting and aligning to these experts. So we've been building a network up of a lot of retired steel workers and people who have been working on sort of chemical plants, things like that. And we've been bringing them into the project to make sure that the knowledge isn't lost. A lot of industries gone from the northeast, and we need to make sure that the knowledge doesn't go with it. And then one last thing, I'm probably way over time, am I? Yeah, sorry. How way over?
17 minutes.
Sorry. One last slide, I promise. Just getting back to energy. I think we're making a massive mistake at the moment by cutting the UK fossil fuel energy generation. Basically, we're doing that in a fashion that is preventing us from hitting the targets that we need to make. So, we've got the energy crisis, we've got imported electricity and gas supply, offshore and CO2, we're increasing the cost of everything. Increasing the cost is going to increase the cost of research and manufacturing. That's going to increase the delays that we have in actually getting to the targets that we need to get to. And I think ultimately this 2050 target, it's going to be unreachable because we're cutting corners and we're not actually using energies. The monetary system, the dollar's based on oil. It's all based on energy. Cheap energy is making things happen. That's why we are where we are today, because of cheap energy. And if energy suddenly becomes expensive, that means that everything else is going to become expensive as well. We're not going to be able to afford or develop the things that we need to develop, and we're going to miss this target because it's going to create that extra delay. And I think that also that's been compounded by this increasing financial divide between the ultra-rich, big tech, and the majority of the global population. So, we've got this looming inflation depression that we're currently facing. And that's going to only dwindle the investment that the UK governments and governments around the world can give to R&D to push the energy cause to stop us from destroying the planet, and also I don't need to extrapolate on that. But anyway. That's me. I hope it was interesting. I hope I didn't waffle on too much, but thank you very much for your time. Thank you for listening.
Thanks, David. Well, Richard, you've explained to us very, very clearly the complicated and the complications of sustainable steel. Thank you. And I'm sure everyone here is has enjoyed this evening and is very, very interested in finding out how you proceed with this and what's going to happen in the next few years. Very, very impressed with your presentations, Richard. Thank you. So,
Back next year, I'll give you an update.
you're on. Right, everyone. You've all heard what's been said here. I'm sure you must have a few questions. We have overrun a little bit, I'm sure, but I don't think that's going to spoil us from asking any questions of Richard that I'm sure he can answer. So, do we have anyone?
I've got a minor one, Richard. To do with the plastic issue, we're trying to reduce the landfill. But in the last couple of years, we've had a massive change from putting waste into landfill, putting waste into waste incinerators, which will then generate electricity. A lot of that is still plastic.
Yeah.
So if you want plastic to go into this process, you're going to have to keep demands where they want to burn it, that they can't recycle, but you want to use it for another thing. I just wondered whether that's been factored in any of your research at all.
It has actually, and it's one of the stumbling blocks I think that we have had. It's a very good question, because we don't know what the supply is going to be, and you can imagine if you're a steel company, you don't want to convert your technology to used plastics if in 2 years' time you're going to have to pay a premium for it, or it's going to be it's not going to be available. and it's very difficult to import waste from, you can't import waste into the country, so you can't import plastic waste from other countries to do that. So yet again, I think it's going to have to be people working together, companies working together. We're trying to do it with steel, with scrap. We're trying to get them all to, agree to buy a certain type of scrap that's the best for their process, rather than everybody go for the stuff that's the ultra high quality and end up with a bidding war. And I think there needs to be some sort of a gentleman's agreement of how we actually do that. And also we need to factor in where the best use is. So if the best use is to produce power, then that's fine. But the way things are going with policy, even burning plastics is becoming a naughty thing. So unless these power generators can put the carbon capture and storage on there as well, and they're just venting the CO2, yes, you're getting a second bite of the cherry, but you're actually still, you're still producing CO2. So it could come down to government policy, it could come down to an agreement, but I think no matter where it goes, they do need to have that carbon capture and utilisation of storage as well. It's a very good question, very astute.
Anyone else, any questions?
I've got two questions on YouTube. John Beatty, are there similarly innovative projects investigating alternative materials? I'll give you a second whilst you're thinking about that. Is anyone working with motor manufacturers to develop construction to make subsequent metal separation easier?
Right, I'll answer the first one first. So we're focusing on steel because ultimately it's the high, it's the, by orders of magnitude compared to the metals, it's actually, it's significantly higher, yeah, and it's got more uses, and it's also basically much cheaper to produce the things you need to produce. So effectively we're focusing, is it on? Yeah. We're focusing on steel, but part of that is we're trying to work as closely as we can with these other metal manufacturing companies, because especially with the scrap side of things, we're really sort of focusing on extracting those different materials, metals, and trying to help them to reuse those and reduce the financial cost of doing that. And the second one, is anybody working on
Alternative motor design.
alternative motor design? One last one for the other one as well. I don't know if you meant sort of like composites as well, but a lot of composite materials are much more difficult to recycle, and we're trying to, even though they do have properties sort of on the first life cycle of wherever the product is, we're really trying to dissuade that, because obviously once that life cycle's over, it becomes very difficult or environmentally unfriendly and costly to actually recycle and use those things again and then produce them. And then the other one, yes, there is. So Jan Godsell, Professor Jan Godsell, who was working on one of our tasks, recently moved to Loughborough. She's really sort of focusing on that side of things, and I can give him more information because I'm going to waffle on a bit forever. If he gets into, I mean, I don't know if you can pass me an email address on or something. I'm happy with that, and I can answer any question he has.
Well, thank you very much, Richard.
I'm sure I saw your hand up.
You did. You did.
Just a sort of observation, really. It's a bit of a paradox, really, that the government and the politicians are pushing the green agenda. Let's get rid of fossil fuels, etc. When they're relying upon you guys as a technocrats to come up with the magic rabbit over the hat. And yet, they're not pushing anything on R&D. So it's sort of
It is difficult, and I think they've put the cart before the horse. Because it's almost like you've got one aspect of, okay, if you say we've got 50 years of using fossil fuels, are people really going to start to push and make sure we make the changes? But then we've got a crisis where they're saying, we haven't got the energy now, we haven't got the raw materials now, you've just got to do it. It's almost like it's make or break. And the amount of R&D that does, I mean, this country, for instance, so if you look at Belgium, they recently put $1 billion into ArcelorMittal plant to help them to convert from blast furnace to using green technology. We've got, 32 million for this, and it's spread across everything. And then, there's the government has given some subsidies to UK steel companies, but it's nowhere near the level that other countries are doing it. So I think the UK are just expecting good old British ingenuity is going to solve the problem, and I'm not so sure it is.
Yeah, what's the last allowing free market economy with the vested interest pushing up. But you mentioned 50 years. There's one who has been married for 50 years. I'll tell you how quickly it goes up.
Yeah.
So get cracking on my yeah.
It's,
Wasn't that
it's 20. It's 28 years now, isn't it? Because it's 2050s. It's getting close.
Wonderful, right.
Thank you very much.
Everyone.
Thank you.
Richard, you've excelled yourself
Oh,
here
thank you
tonight.
very much.
Thank you. But of course, I'd like to call on Norman Jackson here to give a vote of thanks for your presentation this evening. Norman?
Ladies and gentlemen, Dr. Curry, I'm very fortunate here in this that I will stand as a speaker that we are able to get going on. Don't be upset by the number of people here tonight. I'm sure there will be a lot of other people looking on the way. COVID has a lot of answers. But I found it to talk very, very interesting indeed. As part of we are part of a national organisation, we are a local society. And the topic for this year is sustainability in your forecast, critically now to the main in that place here. You give us a good insight into the 9 projects that we have here. And I think the detail of this again, dealing with the scrap side of things, which is obviously your baby.
It is.
I think that the everything the challenges that are there. One thing that I would say is quite, and Bill touched on it there, quite ironic. That the 2 steel companies that we have in this country, one doing by China and the other doing by India. Now, the events that are taking place at the present time, which is leading to the increase in prices of everything, is indicative of the way that we have to modify our thinking. And as far as happens to some of these figures that people are quoting just from personal use, and obviously carbon reduction and the way of doing it, football matter. Because unfortunately I see very little evidence of accountability that people are promising these days for accountability that our matter of how things are doing. And I see no evidence of this anyway. And I've worked in China and India extensively. And I can tell you now, when they're trying, we are not coming to do. But thank you very much for coming along. And on behalf of the members here and those online, I'd like to show our appreciation and
Absolutely. Wonderful.
It's the quality, not the quantity, as well, isn't it?
Well, you managed both.
No, I'm just talking about the audience.
Oh, yes, in that case, yes. Right, well, there we are. Now, well, what's left? Yes, to call on Andrew, if he's available, to give us details of the forthcoming events and such like. Andrew?
Yeah, I was going to ask a question myself, but you cut me off. All I'll say is my colleague is going to be over the moon that you're about the small modular reactors. They're definitely the way forward, and certainly some of our members have also been working on all sorts of things to do with algae. So we should definitely get in touch with them because it all sounds excellent. But hopefully I'll see you soon. So yes, just whip through the notices again. March lecture is going to be by Professor Jeroen van Hunen on modelling mine water heat extraction. Big topic at the moment, and one that our institute is fully behind. Not sure it could power a blast furnace though, but it'd be interesting to see. April lecture and hopefully a field trip as well to the geotechnical engineering of the A1. Further details to coming, but we're nearly fixed that. And of course the main lecture. What better advert could there be than you've already mentioned Professor Andrew Gallant once this evening, come and meet the man himself in May. And don't forget, we'll also be releasing details of our field trip to go and see the location of the discovery of the giant millipede. Again, look out for that. Lots and lots coming up, Steve. So I'll hand back to you.
Yes, well, thank you very much, Andrew. You've explained everything there. I'm sure everyone here is looking forward to the future and seeing some of these presentations, and in fact, seeing all of these presentations. That's great. Well, thank you very much, everyone, for attending here in the hall, and thank you for everyone online, and thank you for the questions you've given forward to. So all I can say now is have a safe journey home. If you could, please remember to sign on to the logs if you haven't done so already. But thank you very much for coming. Good night.
And don't forget about the annual dinner.
And don't forget about the annual dinner.
Where's one of these membership forms anyway?
Yes.
I'll fill one in.
I think we have some...
Is that right?
Oh, yes. Good. Lovely. I'll just go and...